All right, so let's do a proof of the product rule. So let's let t for Toby of x equal f of x times g of x. So we have a function that is made up of the product of two other functions. So if we use the definition of the derivative, then t prime of x would be the limit as h goes to 0 of t of x plus h minus t of x over h. This is just using the standard definition of the derivative that we have been using. So t of x plus h, because t of x is the product of f of x and g of x, is just going to be equal to the limit here as h goes to 0 of f of x plus h, g of x plus h, and then the t of x is just f of x, g of x. All of that over h, okay? Now, this is the part that is interesting, okay? We're going to add 0 to this by taking two terms, one of them positive and one of them negative, that would cancel each other out. And at first, it's going to look like, why on earth would we do this? But it will make sense in a second. So we have this first term, and then we are going to subtract f of x plus h times g of x, and then we are going to come back and add that same term. Now we can do this because our net gain here is 0. We're adding nothing to it. And so why are we doing it, right? All of this, world's biggest numerator, over h. Okay, so now we are going to regroup here. We've got the limit as h goes to 0. Both of these terms have an f of x plus h in them. So we are going to say that this is f of x plus h times g of x plus h minus g of x over h. Again, what I'm doing is taking these first two terms, one of them that I had from the very beginning and one of them that I added in, and each of them have an f of x plus h in it. I'm factoring the f of x plus h out, and this is what's left over. On the last two terms, what I have in common is a g of x. So I'm going to factor that out. So I've got g of x. And then what's left behind here is f of x plus h minus f of x over h. And now maybe it's a little bit more clear why we added and subtracted those terms, because we're putting an f of x plus h in here that's common to the f of x plus h on the first term. And then we got a g of x, which is common to the g of x down here. Okay, so what this is going to equal here is this limit as h goes to 0 of g of x plus h minus g of x over h. And then the limit as h goes to 0 of f of x plus h, if I put 0 in there, that's just going to be f of x. So really what we have here is f of x times that. G of x as h goes to 0 is going to be just g of x, okay? And I'm going to think of this limit here as, I'm going to break the limit down by the rules that we have for limits, that I can do the limit of this first term plus the limit of the second term. So we're going to come back here with plus g of x times the limit as h goes to 0 of what I've got here, okay? Now, if I look at these limits, they should look familiar, because this first limit right here, okay, that's just g prime of x. If I asked you what the derivative of g of x was, and I wanted it in the definition of the derivative kind of format, this is how I would write it up. The limit as h goes to 0 of g of x plus h minus g of x over h. So what I have in this first part here is I've got my t prime of x, is equal to f of x times the g prime, which I'm getting out of this limit, plus g of x. And then the limit down here, the second limit, okay, this is just the derivative of f of x. Okay, so that's coming in here as f prime of x. And so what you're left with is the product rule. So if I start out with a t of x that is the product of two functions, f of x times g of x, the result, the derivative here is going to be the first function times the derivative of the second, plus the second function times the derivative of the first. And that is known as the product rule.